Tonight, we're going to talk about a star that represents both our greatest hope and our harshest limit. The nearest star to our Sun, just 4.24 light-years away. A distance that seems small when you're talking about the cosmos. Close enough that scientists have detected planets orbiting it. Close enough that we can study it in detail with telescopes. Close enough that some people dream about sending probes there within our lifetimes. But here's the truth that's going to reshape how you think about space travel and our place in the universe. This star might as well be on the other side of infinity. Despite being our closest stellar neighbor, it represents a barrier that may prove forever insurmountable. And by the end of tonight, you're going to understand exactly why even the nearest star may be permanently out of reach. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The star we're talking about is called Proxima Centauri, and it's not like our Sun. It's a red dwarf star, much smaller, much dimmer, much colder. If you could place the Sun and Proxima Centauri side by side, the difference would be stark. The Sun has a diameter of about 864,000 miles. Proxima Centauri has a diameter of only about 120,000 miles. That makes it roughly 1/7 the Sun's width. In terms of mass, Proxima Centauri weighs in at only about 12.5% of the Sun's mass. It's tiny by stellar standards. The Sun is classified as a G-type main sequence star. Proxima Centauri is an M-type red dwarf. These differences matter enormously. They determine everything about how the star behaves, how bright it shines, how long it will live, and what kind of environments exist around it. Red dwarfs are the most common type of star in the galaxy. They make up roughly 70% of all stars. But they're incredibly dim compared to stars like our Sun. Proxima Centauri's luminosity is only about 0.17% of the Sun's luminosity, less than 0.2%. That means even though it's much closer to us than any other star besides the Sun, you can't see it with your naked eye, not even close. You need a telescope. Even with a small telescope, it appears as just a faint point of light, a 13th magnitude star. For reference, the faintest stars you can see with your naked eye under perfect dark sky conditions are about 6th magnitude. Each magnitude represents a brightness difference of about 2.5 times. So 6th magnitude to 13th magnitude is a difference of 7 magnitudes, which translates to roughly 630 times fainter than the dimmest stars visible to the unaided eye. Proxima Centauri is out there, closer than any other star, and we can't even see it without optical aid. Now, Proxima Centauri isn't alone in space. It's part of a triple star system called Alpha Centauri. The other two stars in this system are Alpha Centauri A and Alpha Centauri B. These two stars orbit each other in a binary pair. They're both much more like our Sun than Proxima is. Alpha Centauri A is slightly larger and brighter than the Sun. Alpha Centauri B is slightly smaller and dimmer. Together, they form a bright pair, visible from the southern hemisphere as a single point of light to the naked eye. In fact, Alpha Centauri is the third brightest star in Earth's night sky. Proxima Centauri orbits this binary pair at a tremendous distance. The current distance between Proxima and the Alpha Centauri AB pair is about 13,000 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. So 13,000 astronomical units is about 1.2 trillion miles. Proxima is gravitationally bound to Alpha Centauri A and B, but just barely. Its orbit around the pair takes roughly 550,000 years to complete, maybe longer. The orbit is so slow and so distant that astronomers aren't entirely certain of its exact parameters. There's even some debate about whether Proxima is genuinely bound to the system or if it's just passing through, a chance encounter that will eventually see it drift away. Most evidence suggests it is bound, but the point stands that this is a very loose association. The reason we call it Proxima Centauri is because of its distance from us. Proxima means nearest in Latin. Of the three stars in the Alpha Centauri system, Proxima is the closest to Earth. It's about 4.24 light-years away. Alpha Centauri A and B are slightly farther, about 4.37 light-years away. So Proxima holds the title of nearest star to our solar system. It's been our closest stellar neighbor for thousands of years, and it will remain so for many thousands more. But that distance is what we need to examine closely. 4.24 light-years. What does that actually mean in terms we can understand? A light-year is the distance light travels in 1 year. Light moves at about 186,000 miles per second. In 1 year, traveling at that speed continuously, light covers about 5.88 trillion miles. So 4.24 light-years is about 24.9 trillion miles. Let's try to put that in perspective. The Apollo spacecraft that carried astronauts to the moon traveled at speeds up to about 25,000 miles per hour. At that speed, it would take roughly 114,000 years to reach Proxima Centauri. The fastest spacecraft humanity has ever built is the Parker Solar Probe. At its peak velocity, when it's diving close to the Sun and using solar gravity to accelerate, it reaches speeds of about 430,000 miles per hour. That's incredibly fast. It's roughly 1/600th the speed of light. At that speed, the Parker Solar Probe could reach the Moon in about 30 minutes. But even at this record-breaking velocity, it would still take roughly 6,600 years to reach Proxima Centauri. If you had launched the Parker Solar Probe toward Proxima Centauri, when it actually launched in 2018, it would arrive in the year 8618. It would still be in transit, crossing the vast empty darkness between stars. And that's using the fastest spacecraft we've ever built. This is the problem. The distance to even the nearest star is so enormous that it dwarfs anything in human experience. We're not talking about a journey across an ocean or even across a solar system. We're talking about a gulf so wide that crossing it would take thousands of years with our current technology. And Proxima Centauri is the closest star. Every other star is farther. Now, you might think, well, we just need faster spacecraft. If we can build something faster, something that can travel at a significant fraction of light speed, then we can reach Proxima Centauri within a human lifetime. And technically, you're right. If you had a spacecraft that could travel at 10% of the speed of light, the trip to Proxima Centauri would take about 42 years. Still a long time, but within a human lifespan. If you could reach 50% of light speed, the trip would take about 8.5 years. If you could somehow reach 90% of light speed, it would take less than 5 years. So, the question becomes, can we build spacecraft that travel at these speeds? The answer is far more complicated and far more discouraging than you might expect. Let's talk about propulsion. How do you make something go fast in space? On Earth, we're used to pushing against something. Cars push against the road. Boats push against water. Airplanes push against air. But in space, there's nothing to push against. Space is a vacuum. So spacecraft use rockets. Rockets work by throwing mass out the back at high speed. The reaction to this ejected mass pushes the rocket forward. It's Newton's third law. For every action, there's an equal and opposite reaction. This is how all our current spacecraft work. They carry fuel, they burn it, and they expel the exhaust out the back to generate thrust. The problem is that to go faster, you need more fuel, and fuel has mass. So, the more fuel you carry, the heavier your spacecraft becomes, which means you need even more fuel to accelerate that heavier spacecraft. This is called the tyranny of the rocket equation. It's a fundamental constraint that makes high-speed space travel incredibly difficult. Let's look at some numbers. The Saturn V rocket that launched the Apollo missions to the Moon weighed about 6.2 million pounds at liftoff. Of that, roughly 5.7 million pounds was fuel. The actual payload, the command module, lunar module, and service module that went to the Moon weighed only about 98,000 pounds. So, about 92% of the rocket's mass was fuel, and only about 1.6% was the actual spacecraft. The rest was the rocket structure itself. And that was just to get to the Moon, a 3-day journey at relatively modest speeds. To reach Proxima Centauri at 10% of light speed would require energies vastly beyond anything we can currently produce. Some physicists have calculated that accelerating even a small probe, something the size of a postage stamp weighing just a few grams, to 10% of light speed would require energy comparable to a large nuclear bomb. And that's just for a tiny probe. For a spacecraft large enough to carry scientific instruments, or even more ambitiously, human passengers, the energy requirements become astronomical. You would need fuel masses many times greater than the mass of the spacecraft itself. And the faster you want to go, the worse the problem becomes. To reach 50% of light speed, you'd need exponentially more fuel. To reach 90% of light speed, the fuel requirements become absurd. You'd need fuel masses larger than planets. It's simply not feasible with chemical rockets. Chemical rockets, the kind we use now, burn fuel and oxygen to create hot gases that are expelled out the back. They're reliable and well understood, but they're also fundamentally limited. The maximum exhaust velocity you can achieve with chemical rockets is only about 3 to 5 miles per second. That's fast, but nowhere near fast enough for interstellar travel. So, scientists have proposed other types of propulsion systems. Nuclear rockets, for example. Instead of chemical combustion, you use a nuclear reactor to heat a propellant, usually hydrogen, to extremely high temperatures, and then expel it out the back. This can give you exhaust velocities of about 5 to 10 miles per second. Better than chemical rockets, but still not nearly enough. Ion drives are another option. These use electricity to ionize atoms and accelerate them to very high speeds using electric and magnetic fields. Ion drives can achieve exhaust velocities of 20 to 60 miles per second. Much better. The problem is that ion drives produce very little thrust. They can accelerate a spacecraft slowly over long periods of time, but they can't give you the quick burst of speed you'd need for a fast trip to another star. There have been proposals for even more exotic propulsion systems. Nuclear pulse propulsion, for instance. This involves detonating nuclear bombs behind the spacecraft and riding the shockwave. It sounds insane, and it kind of is. But it was seriously studied in the 1950s and 60s under a project called Orion. The idea is that you drop a nuclear bomb out the back of your spacecraft, detonate it, and the explosion would hit a large shock absorber plate on the back of the ship, pushing it forward. You'd repeat this process, bomb after bomb, each explosion giving you another push. Calculations suggested that a spacecraft using nuclear pulse propulsion could reach speeds of about 3 to 5% of light speed. That would get you to Proxima Centauri in maybe 80 to 140 years. Still a long time, but much better than thousands of years. The obvious problems are the engineering challenges of building a spacecraft that can withstand repeated nuclear explosions, the political and environmental problems of detonating nuclear weapons in Earth's atmosphere or orbit, and the sheer number of nuclear bombs you'd need to carry. For these reasons, nuclear pulse propulsion has never been built. Another idea is antimatter propulsion. When matter and antimatter meet, they annihilate each other, converting their entire mass into energy. According to Einstein's famous equation, E equals mc squared. This is the most efficient energy conversion possible. If you could harness matter-antimatter annihilation for propulsion, you could theoretically achieve very high exhaust velocities, close to the speed of light. The problem is antimatter. We can produce tiny amounts of it in particle accelerators, but it's incredibly expensive and difficult. Producing just 1 gram of antimatter would cost trillions of dollars with current technology. And storing antimatter is another nightmare. Antimatter annihilates instantly upon contact with normal matter, so you need to keep it suspended in magnetic or electric fields inside a perfect vacuum. Any containment failure means instant annihilation. For all these reasons, antimatter propulsion remains purely theoretical. Then there's the concept of a fusion rocket. Nuclear fusion is the process that powers the sun. Fusing light atomic nuclei, like hydrogen, into heavier nuclei releases tremendous amounts of energy. If we could build a fusion rocket, it could theoretically provide very high exhaust velocities, perhaps 10% of light speed or more. The catch is that we haven't mastered controlled nuclear fusion yet. We've been trying for decades. Experimental fusion reactors have been built, and some have achieved brief moments where the fusion reaction produces more energy than it consumes. But we're still far from a practical, sustained fusion reactor. And even if we solve fusion for power generation, adapting it for rocket propulsion introduces a whole new set of challenges. So, where does this leave us? With our current technology, reaching Proxima Centauri would take tens of thousands of years. With plausible near-future technology, like advanced ion drives or nuclear electric propulsion, we might cut that down to thousands of years. With highly speculative technologies like nuclear pulse propulsion or fusion rockets, we might get down to hundreds or a few decades. But none of these are easy. None of them are close to being realized. And all of them require enormous investments of resources, energy, and time. But let's say, for the sake of argument, that we solve the propulsion problem. Let's imagine we develop a fusion rocket or some other advanced propulsion system that can accelerate a spacecraft to 10% of light speed. That would get us to Proxima Centauri in about 42 years, within a human lifetime. Are we done? Can we declare victory and start packing for the trip? Not even close. Because speed is only one of the problems. There are many others. Let's talk about navigation. Proxima Centauri is 4.24 light-years away. That's roughly 24.9 trillion miles. At 10% of light speed, you're traveling at about 18,600 miles per second. At that speed, if your navigation is off by even a tiny fraction of a degree, you'll miss your target by billions of miles. Space is vast and mostly empty. Stars look like they're close together in the sky, but that's an illusion created by distance. In reality, they're separated by enormous gulfs of emptiness. If you're aiming for Proxima Centauri and you miss, there's nothing else nearby to hit. You'll just sail off into the void, lost forever. So, your navigation needs to be extraordinarily precise. You need to know your position and velocity with incredible accuracy. You need to account for the motion of Proxima Centauri itself, because stars move. Proxima Centauri is moving relative to us at about 14 miles per second. Over the course of a 42-year journey, it will have moved quite a bit. You need to aim, not for where it is now, but for where it will be when you arrive. Then, there's the problem of course corrections. Even with perfect initial navigation, tiny errors accumulate over time. A small thrust from a micrometeoroid impact, a slight imbalance in your propulsion system, the gravitational pull of distant stars, all of these can nudge you off course. You'll need to make corrections along the way. But at 10% of light speed, even small course corrections require enormous amounts of energy. And every bit of fuel you use for corrections is fuel you're not using for the primary journey. Then, there's the problem of communication. Let's say you launch a probe toward Proxima Centauri. It's traveling at 10% of light speed. After 1 year, it's traveled about 0.1 light-years. If it sends a radio signal back to Earth, that signal travels at the speed of light. But the probe is already 0.1 light-years away, so the signal takes 0.1 years to reach Earth. By the time we receive it, the probe is even farther away. After 10 years, the probe is 1 light-year away. A signal from the probe takes 1 year to reach us. By the time the probe reaches Proxima Centauri after 42 years, it's 4.24 light-years from Earth. Any signal it sends takes 4.24 years to reach us. If we want to send a command to the probe, our signal takes 4.24 years to get there. So there's a round-trip communication delay of 8.5 years. This makes real-time control impossible. Any probe we send to Proxima Centauri will need to be largely autonomous. It will need to make its own decisions, navigate on its own, conduct its own science. We can send it instructions, but by the time those instructions arrive, the situation may have changed completely. Now, let's talk about survival. Space is not a friendly environment. Even interplanetary space, the region between planets in our solar system, is filled with hazards. But interstellar space, the vast emptiness between stars, is even more dangerous in some ways. First, there's radiation. Space is filled with cosmic rays, high-energy particles accelerated by supernova explosions, black holes, and other violent cosmic events. These particles travel at nearly the speed of light. When they hit matter, they can cause damage at the atomic level. In the solar system, Earth's magnetic field and atmosphere protect us from most cosmic rays. Spacecraft in low Earth orbit are partially protected by Earth's magnetic field. But in interstellar space, there's no protection. A spacecraft traveling to Proxima Centauri would be bombarded by cosmic rays continuously for decades. This radiation can damage electronics, degrade materials, and if there are any biological organisms aboard, living cells. Shielding against cosmic rays is difficult because the particles are so energetic. Thick, metal shielding helps, but it also adds mass, which makes your spacecraft heavier and harder to accelerate. And even thick shielding doesn't stop everything. Some cosmic rays are so energetic they can penetrate meters of solid material. Then there's the problem of micrometeoroids. These are tiny particles of dust and rock floating in space. In the solar system, there's a fair amount of this material. Debris left over from the formation of planets, fragments from asteroid collisions, dust from comets. But even in interstellar space, there are dust grains. They're rare, but they exist. At normal orbital speeds, a micrometeoroid impact is a minor problem. It might chip the paint off your spacecraft or create a tiny crater. But at 10% of light speed, even a grain of dust becomes a devastating projectile. At 18,600 miles per second, a dust grain the size of a sand particle carries as much kinetic energy as a bullet. A pebble-sized object would hit with the force of a large bomb. Any impact at these speeds would be catastrophic. So your spacecraft needs shielding. But again, shielding adds mass. And the faster you go, the worse the problem becomes. At 50% of light speed, even smaller particles become lethal. There have been proposals for magnetic shields that would deflect charged particles, or for placing a sacrificial shield in front of the spacecraft. A thick slab of material that would absorb impacts and protect the main spacecraft behind it. But all of these solutions add complexity and mass. Then there's the problem of power. A spacecraft traveling to Proxima Centauri needs power for its systems. Communication equipment, navigation systems, scientific instruments, life support if there are passengers, all of these require electricity. In the solar system, spacecraft often use solar panels. The sun provides abundant energy, and solar panels convert sunlight into electricity. But as you move away from the sun, solar power becomes less and less effective. The intensity of sunlight follows an inverse square law. Double your distance from the sun, and the sunlight becomes 4 times weaker. Triple the distance, and it becomes 9 times weaker. By the time you're at Jupiter's distance, about 483 million miles from the sun, sunlight is only about 4% as intense as it is at Earth. Solar panels still work, but they need to be much larger to generate the same amount of power. The Juno spacecraft orbiting Jupiter has 3 enormous solar panel arrays stretching nearly 66 feet in length. These massive panels generate only enough power to run a few household appliances. At Saturn's distance, about 890 million miles, sunlight is only 1% as intense as at Earth. The Cassini spacecraft used nuclear power instead of solar panels, because solar power was impractical that far out. Beyond Saturn, in the outer solar system where Uranus and Neptune orbit, solar power is essentially useless. And in interstellar space, there is no sunlight. You're traveling through darkness, far from any star. The sun behind you has faded to just another bright point of light among millions. Proxima Centauri ahead is still too far away to provide any meaningful energy. Solar panels won't work. So, you need another power source. Nuclear power is the obvious answer. Radioisotope thermoelectric generators, or RTGs, use the decay of radioactive materials to generate heat, which is then converted to electricity. the process is elegant in its simplicity. A chunk of radioactive material, typically plutonium-238, sits in a protective container. As the plutonium atoms decay, they release heat. Thermocouples, devices that convert temperature differences into electricity, surround the plutonium. One side of the thermocouple is hot from the plutonium, the other side is cold from exposure to space. This temperature difference generates a small electric current. It's not much power, typically only a few hundred watts, but it's reliable, continuous, and doesn't require any moving parts. RTGs have powered many deep space missions. The Voyager 1 and Voyager 2 probes, launched in 1977, both carry RTGs. 47 years later, they're still operating, still sending data back to Earth from beyond the edge of the solar system. The Curiosity rover on Mars uses an RTG. The Cassini mission to Saturn used RTGs. The New Horizons mission to Pluto used an RTG. They work. They're proven technology. The problem is that RTGs decay over time. Plutonium-238 has a half-life of 87.7 years. That means, after 87.7 years, half of your plutonium has decayed. The RTG produces half as much heat, and therefore half as much electricity. After another 87.7 years, it's down to a quarter. For Voyager, launched in 1977, the RTGs are now producing significantly less power than they did at launch. NASA has had to shut down various instruments and heaters to conserve the remaining electricity. Eventually, probably within the next decade or so, the power will drop too low to run any instruments. The Voyagers will go silent, drifting through interstellar space with their messages to any alien civilization that might find them, but with no power to communicate with Earth. For a mission to Proxima Centauri that takes 42 years or more, you'd need RTGs with very long-lived isotopes. Plutonium-238 works for missions lasting a few decades, but for longer missions you'd need something different. Or you'd need a lot of RTGs, more than you need at the start, so that even as they decay, you still have enough power. But RTGs have limited power output. Even a large RTG only produces a few hundred watts. For comparison, a typical household in the United States uses about 1,000 watts continuously, or about 1 kilowatt. A spacecraft with sophisticated scientific instruments, communication systems, computers, and possibly life support would need several kilowatts at least. That means multiple RTGs, which adds mass. And mass, as we've discussed, is the enemy of efficient space travel. The alternative is a nuclear fission reactor. A fission reactor can produce much more power than an RTG. Hundreds of kilowatts, or even megawatts. The Soviet Union flew nuclear reactors on some of their satellites in the 1970s and 80s. The United States developed reactor designs for space use, but never flew them. A space-rated nuclear reactor would be compact, perhaps the size of a large trash can, and could produce enough electricity to power a small town. For an interstellar mission, this would be ideal. Plenty of power for all systems, with fuel that lasts for years or decades. But reactors are complex. They require cooling systems to remove excess heat. They need shielding to protect the spacecraft and crew from radiation. They have moving parts, control rods that adjust the reaction rate, pumps that circulate coolant. All of this adds mass and complexity. And there's the risk of failure. If the reactor malfunctions, you could lose all power. Or worse, you could have a meltdown. Though in space, the consequences would be different than on Earth. No atmosphere to carry radioactive fallout, but the spacecraft itself would be contaminated. These are solvable problems, but they require careful engineering and extensive testing. And nuclear reactors in space are politically sensitive. The idea of launching a spacecraft with a nuclear reactor makes many people nervous. What if the launch fails and the reactor comes crashing back down to Earth? What if it breaks apart in the atmosphere and scatters radioactive material? These are legitimate concerns, though modern reactor designs include multiple safety features to prevent such scenarios. Still, public opinion matters, and convincing the public that nuclear-powered spacecraft are safe is a challenge in itself. There's also the problem of heat. In space, getting rid of excess heat is difficult. On Earth, heat dissipates into the air through convection and conduction. The air around a hot object heats up, rises, and carries the heat away. Water cooling works similarly, using flowing liquid to transport heat from one place to another. But in space, there's no air. There's no atmosphere to carry heat away through convection. The only way to lose heat is through thermal radiation. Hot objects emit infrared radiation, which carries energy away into space. This is how spacecraft cool themselves. They have radiators, large panels that get hot and radiate that heat away as infrared light. But radiation is a relatively slow process compared to convection. On Earth, you can cool a hot engine quickly by blowing air over it or circulating water through it. In space, you're limited to radiation, which means you need large radiator panels to dissipate significant amounts of heat. A nuclear reactor generates a lot of heat. Only about 30 to 40% of the energy from nuclear fission is converted to electricity. The rest becomes waste heat that needs to be radiated away. For a reactor producing 100 kilowatts of electricity, you'd have roughly 200 kilowatts of waste heat. That requires radiator panels with a total surface area of dozens or hundreds of square meters, depending on their temperature and efficiency. More mass, more complexity, more things that can break. The radiators need to be deployed after launch, which adds mechanical complexity. They need to remain oriented properly to radiate heat into space rather than toward the sun or toward sensitive parts of the spacecraft. And they're vulnerable to damage from micrometeoroids or radiation. A puncture in a liquid-cooled radiator could cause coolant to leak, crippling the cooling system. So you need redundancy, backup systems, multiple independent cooling loops. All of this engineering is doable. We've built spacecraft with complex thermal management systems before. The International Space Station has enormous radiator panels that glow visibly in infrared images. But for an interstellar mission, every system needs to work reliably for decades without maintenance or repair. That's a much higher bar than for missions in Earth orbit or even to Mars, where we can potentially send supplies or rescue missions if something goes wrong. For Proxima Centauri, there's no backup plan. Once the spacecraft launches, it's on its own. All of these challenges, propulsion, navigation, communication, radiation, micrometeoroids, power, heat dissipation, are enormous. Each one alone would be a significant engineering problem. Together, they make interstellar travel seem almost impossible with current or near-future technology. But let's continue the thought experiment. Let's say we solve all of these problems. We build a spacecraft with advanced propulsion that can reach 10% of light speed. We give it robust shielding against radiation and impact. We equip it with long-lasting power systems, autonomous navigation, and sophisticated communication equipment. We launch it toward Proxima Centauri. 42 years later, it arrives. What does it find? This is where things get interesting. Because Proxima Centauri is not just a star. It's a star with planets. In 2016, astronomers announced the discovery of Proxima Centauri b, a planet orbiting Proxima Centauri. It was detected using the radial velocity method. As a planet orbits a star, its gravity tugs on the star slightly, causing the star to wobble. This wobble shifts the star's light toward the red or blue end of the spectrum, depending on whether the star is moving away from us or toward us. By measuring these shifts, astronomers can infer the presence of a planet and determine some of its properties. Proxima Centauri b is roughly 1.2 times the mass of Earth. It orbits Proxima Centauri at a distance of about 4.5 million miles. That sounds far. But remember, Proxima Centauri is much smaller and dimmer than the Sun. At this distance, Proxima b receives roughly the same amount of energy from its star that Earth receives from the Sun. This puts it in what astronomers call the habitable zone, the region around a star where temperatures are right for liquid water to exist on a planet's surface. Liquid water is considered essential for life as we know it. So the discovery of Proxima b in the habitable zone was exciting. Here was a planet, roughly Earth-sized, orbiting in the habitable zone of the nearest star to our Sun. Could it have life? Could it be habitable? The answer is complicated. Proxima b orbits very close to its star. At 4.5 million miles, it's much closer than Mercury is to our Sun. Mercury orbits at about 36 million miles. Because Proxima b is so close, it's likely tidally locked. This means one side of the planet always faces the star, and the other side always faces away. Just like the Moon is tidally locked to Earth, always showing us the same face. On a tidally locked planet, one hemisphere would be in perpetual daylight, the other in perpetual darkness. The day side would be scorching hot. The night side would be freezing cold. There might be a narrow band between the two, a twilight zone, where temperatures are moderate. This is where liquid water and potentially life might exist. But there's another problem. Red dwarfs, like Proxima Centauri, are known for being volatile. They produce frequent and powerful stellar flares. These flares release intense bursts of radiation and charged particles. On Earth, we're protected from solar flares by our magnetic field and atmosphere. But if Proxima b doesn't have a strong magnetic field, these flares could strip away its atmosphere over time. They could also bathe the planet's surface in lethal radiation, making life as we know it impossible. Observations of Proxima Centauri have shown that it does indeed produce powerful flares. Some of these flares are much stronger than anything the Sun produces. During a flare, the star's brightness can increase significantly for a few minutes, then fade back to normal. But in those few minutes, the amount of high-energy radiation hitting Proxima b would be enormous. If Proxima b has an atmosphere and a magnetic field, it might be protected. If it doesn't, it's probably a barren, irradiated rock. We don't know yet. We can't directly image Proxima b with current telescopes. It's too small and too close to its star. All we have is the radial velocity data that tells us it exists and gives us a rough idea of its mass and orbit. In 2019, astronomers announced the possible detection of a second planet, Proxima Centauri c. This planet, if it exists, is larger, perhaps several times the mass of Earth, and orbits farther out, beyond the habitable zone. It would be a cold, inhospitable world. The detection of Proxima c is less certain than Proxima b. More observations are needed to confirm it. And in 2020, there were hints of a possible third planet, Proxima d, orbiting even closer to the star than Proxima b. This one would be smaller, perhaps only about a quarter of Earth's mass. If it exists, it's also tidally locked and probably too hot for life. So, Proxima Centauri appears to have a planetary system. At least one planet, possibly three. One of them, Proxima b, is in the habitable zone. This makes Proxima Centauri an obvious target for our hypothetical interstellar mission. If we're going to send a probe to another star, why not send it to a star with planets? Why not a star with a potentially habitable planet? But here's where the challenges multiply even further. Let's say our probe reaches Proxima Centauri after 42 years. It's traveling at 10% of light speed. That's 18,600 miles per second. How does it stop? If the probe just flies past Proxima Centauri at that speed, it won't be able to study the system in detail. It will zip through the system in a matter of hours or days, barely enough time to take a few snapshots before it's gone. To do serious science, to study the planets, to look for signs of life, the probe needs to slow down. It needs to enter orbit around Proxima Centauri or around Proxima b. But slowing down requires energy, just as much energy as it took to speed up in the first place. You need to fire your rockets in the opposite direction, burning fuel to decelerate. And if you've already burned most of your fuel accelerating to 10% of light speed, where are you going to get the fuel to slow down? This is called the delta V problem. Delta V is the total change in velocity your spacecraft needs to make. If you want to accelerate to 10% of light speed and then decelerate back to zero, your total delta V is 20% of light speed. You need enough fuel to accomplish both maneuvers. And as we discussed earlier, fuel has mass, and carrying more fuel makes your spacecraft heavier, which requires even more fuel. The rocket equation becomes even more punishing. One proposed solution is to carry fuel, but use it only for deceleration. You accelerate using some other method, like a laser sail, and save your onboard fuel for slowing down at the destination. A laser sail is a large, ultra-thin, reflective sail. A powerful laser beam from Earth hits the sail, and the photons bounce off, transferring momentum and pushing the sail forward. With a powerful enough laser and a lightweight enough spacecraft, you could accelerate to a significant fraction of light speed without carrying fuel. The challenge is that the laser needs to be incredibly powerful. We're talking about a laser with a power output comparable to a large power plant, and it needs to stay focused on a tiny sail that's getting farther and farther away. The breakthrough Starshot project, proposed by physicist Philip Lubin and funded by investor Yuri Milner, envisions exactly this. A fleet of tiny probes, each weighing only a few grams, equipped with small sails. A massive array of lasers on Earth would accelerate these probes to about 20% of light speed. At that speed, they could reach Proxima Centauri in about 20 years. The probes would be too small to carry much fuel, so they wouldn't slow down. They'd zip through the Proxima Centauri system at high speed, take pictures, collect data, and transmit it back to Earth. Then they'd continue on into the void. One-way missions. This is one of the few interstellar mission concepts that seems remotely feasible with near-future technology. The probes would be tiny, barely more than computer chips with cameras. They couldn't carry much equipment, but they could at least give us a close-up look at another star system. The engineering challenges are still enormous. Building a laser array, powerful enough to accelerate the probes. Designing sails that can survive the intense laser light without burning up. Miniaturizing scientific instruments to fit on a gram-scale probe. Ensuring the probes can communicate back to Earth across 4 light-years with only minimal power. But it's within the realm of possibility. And yet, even this minimalist approach highlights the fundamental problem. Reaching even the nearest star is hard. Incredibly, prohibitively hard. And we're talking about Proxima Centauri, the absolute closest star. Every other star is farther. Barnard's star, the next closest, is about 6 light-years away. Sirius, the brightest star in our night sky, is 8.6 light-years away. Most stars are hundreds or thousands of light-years away. If Proxima Centauri is barely reachable with speculative future technology, those other stars are completely out of reach. This brings us to a sobering realization. Interstellar travel, at least to destinations beyond our immediate stellar neighborhood, may not just be hard. It may be impossible. Not impossible in the sense that it violates the laws of physics. We know it's physically possible to travel to other stars. The laws of physics don't forbid it, but impossible in the practical sense. In the sense that the energy, resources, time, and technological advancement required are so far beyond what we can achieve that it might as well be forbidden. Consider the energy requirements. To accelerate a 1-ton spacecraft to 10% of light speed requires roughly 10 to the power of 18 joules of energy. That's a billion joules. For comparison, the total energy consumption of all of humanity in a year is about 6 times 10 to the power of 20 joules. So, accelerating a 1-ton spacecraft to 10% of light speed would require about 0.2% of humanity's entire annual energy consumption. For one spacecraft, if you want to send a larger spacecraft or a crewed mission, the energy requirements scale up proportionally. A 100-ton spacecraft would require 10 to the power of 20 joules. That's roughly 1/6 of humanity's total annual energy usage. For one mission. And that's just to get there. If you want to slow down at the destination, double it. These numbers are staggering. They suggest that interstellar travel, at least with massive spacecraft, requires a civilization with energy resources far beyond what we currently have. Some scientists have proposed using the power of the sun itself. A Dyson swarm, a hypothetical megastructure consisting of countless solar collectors orbiting the sun, capturing a significant fraction of its energy output. With that much energy, you could power the lasers needed for laser sail missions. You could potentially accelerate larger spacecraft. But building a Dyson swarm is itself an engineering project of almost unimaginable scale. It would require mining asteroids for raw materials, constructing millions or billions of individual solar collectors, positioning them in stable orbits. It's the kind of project that might take centuries or millennia to complete. And even if we built one, we'd still be limited in how fast we could send spacecraft. The speed of light is an absolute limit. Nothing with mass can reach or exceed it. This is a fundamental law of physics, a consequence of Einstein's theory of special relativity. As you accelerate closer and closer to the speed of light, your mass effectively increases, and it requires more and more energy to accelerate further. To actually reach the speed of light would require infinite energy. So there's a hard cap on how fast we can travel. And that cap means there's a limit to how far we can realistically explore within a human lifetime. Even if we could build a spacecraft that travels at 99% of light speed, which is far beyond anything we can currently imagine, it would still take over 4 years to reach Proxima Centauri, over 8 years to reach Barnard's star, nearly 9 years to reach Sirius. And that's one way. If you want to send signals back, add another 4 or 8 or 9 years for the light speed transmission to reach Earth. For more distant stars, the travel times become prohibitive. A star, 100 light-years away, would take over 100 years to reach, even at 99% of light speed. A star, 1,000 light-years away, would take over 1,000 years. This is where time dilation comes into play. According to special relativity, time passes more slowly for objects moving at high speeds relative to a stationary observer. If you're on a spacecraft traveling at 99% of light speed, time for you would pass more slowly than time for people on Earth. The exact factor depends on your speed. At 99% of light speed, time dilation is about a factor of 7. What feels like 1 year to you on the spacecraft is actually 7 years passing on Earth. This means that from the perspective of the spacecraft's passengers, a journey to a star 100 light-years away might only feel like 14 years or so. But on Earth, over a century would have passed. Everyone you knew would be gone. The world would have changed beyond recognition. You'd be a time traveler, moving into the future but unable to return to your own time. For a journey to a star 1,000 light-years away, the time dilation effects would be even more extreme. The passengers might experience a few decades, but on Earth, 1,000 years or more would pass. Civilizations would rise and fall. Technologies would advance beyond imagination. By the time you returned, if you returned, Earth might not even recognize you. This creates a fundamental barrier to interstellar exploration. Not a physical barrier, but a temporal one. You can travel to distant stars, but you're severing your connection to the world you left behind. You're embarking on a one-way journey into the future. For many people, that's an unacceptable cost. And it raises questions about the purpose of such journeys. If you send a crewed mission to a star 100 light-years away, and everyone on Earth will be gone by the time the mission returns, who is the mission for? What's the point? You're not exploring for the benefit of your own civilization. You're exploring for the benefit of some future civilization that doesn't exist yet. There's also the question of obsolescence. If you launch a spacecraft to Proxima Centauri using the best technology available today, and it takes 42 years to get there, what happens if, 20 years into the journey, we develop much better technology? We could launch a second spacecraft that's faster and arrives before the first one. The first spacecraft becomes obsolete, overtaken by its successor. This is sometimes called the weight calculation. If technology is improving rapidly, it might make sense to wait before launching an interstellar mission. Wait until propulsion systems are better, until we can build faster spacecraft. But if you always wait for better technology, you never launch. there's always something better on the horizon. It's a paradox. The only way to resolve it is to decide that the current technology is good enough and commit to the mission. But what if it's not? What if the mission fails because the technology wasn't ready? These are the kinds of dilemmas that make interstellar travel not just a technological challenge, but a philosophical and strategic one. Now, let's talk about the biological challenges of interstellar travel. If we're sending humans, not just probes, the challenges multiply yet again. Humans need air, water, food, warmth, protection from radiation, gravity to maintain bone and muscle health, and psychological stimulation. Providing all of these for a journey lasting decades or centuries is extraordinarily difficult. Let's start with life support. On Earth, we have a biosphere that recycles air and water naturally. Plants produce oxygen. Water evaporates, forms clouds, and falls as rain. Dead organisms decompose and return nutrients to the soil. The system is self-sustaining. On a spacecraft, you need to replicate this. You need to recycle air, removing carbon dioxide and replenishing oxygen. You need to recycle water, purifying wastewater and condensing humidity from the air. You need to grow food, either in hydroponic gardens or through some other method. The International Space Station does some of this. It recycles water and air to a certain extent. But it also relies on regular resupply missions from Earth. For an interstellar journey, there are no resupply missions. You're on your own. Everything you need must be produced on board or carried with you from the start. Carrying decades or centuries worth of food, water, and air is impractical. The mass would be enormous. So, you need closed-loop life support systems. Systems that recycle everything with near-perfect efficiency. Even small losses accumulate over time. If your recycling system is 99% efficient, losing 1% of your water every cycle, you'd run out eventually. Over decades, even tiny inefficiencies become critical. Then there's radiation. We talked about cosmic rays earlier, but for human passengers, the problem is even worse. Radiation damages DNA. It increases the risk of cancer. It can cause acute radiation sickness at high doses. Astronauts on the International Space Station are exposed to higher radiation levels than people on Earth, but they're still partially protected by Earth's magnetic field. On a journey to Proxima Centauri, there's no such protection. You'd need heavy shielding, meters of water or metal to block the radiation. Or you'd need to develop advanced shielding technologies, magnetic fields that deflect charged particles, or pharmaceuticals that repair radiation damage. None of these solutions are easy or well tested. There's also the issue of gravity. In space, without gravity, the human body deteriorates. Bones lose density. Muscles atrophy. The cardiovascular system weakens. Astronauts on the International Space Station exercise for hours every day to counteract these effects, and they still experience significant bone and muscle loss. For a journey lasting decades, the effects would be severe. By the time you arrived at Proxima Centauri, you might be too weak to function. The solution is artificial gravity. You could build a rotating spacecraft. The rotation creates centrifugal force, which simulates gravity. But this adds complexity. The spacecraft needs to be large enough that the rotation doesn't cause disorientation or nausea. It needs to rotate smoothly and continuously for the entire journey. The engineering challenges are significant. Then, there's the psychological challenge. Imagine being confined to a spacecraft for 40 years or more. You can't go outside. There's no fresh air, no open spaces, no nature, just metal walls and recycled air. You're with the same small group of people for the entire journey. There's no escape, no privacy, no relief. The isolation and monotony could drive people insane. Studies of long-duration missions, like Antarctic research stations or long submarine deployments, show that people struggle psychologically. Conflicts arise. Depression and anxiety are common, and those missions last months, not decades. For a mission lasting 40 years, you'd need to select crew members who are extraordinarily psychologically resilient. You'd need to provide entertainment, meaningful work, ways to maintain mental health. Some proposals include suspended animation or cryogenic freezing. Put the crew to sleep for the journey and wake them up when you arrive. This would solve the psychological problem and reduce life support needs. But we don't have the technology to do this. We can freeze cells and embryos, but freezing and reviving a whole human being without damage is still science fiction. Then there's the question of mission duration. 42 years is within a human lifetime, but it's a significant fraction of one. If you're 25 when you launch, you're 67 when you arrive. You've spent most of your adult life in transit, for longer journeys. To stars farther than Proxima Centauri, the mission duration exceeds a human lifespan. You'd need generational ships, spacecraft, where the original crew has children, who grow up on the ship and eventually have children of their own. By the time the ship arrives, the original crew is gone, and it's their descendants who complete the mission. Generational ships raise profound ethical questions. The children born on the ship never chose to be part of the mission. They're born into confinement, destined to spend their entire lives traveling to a destination they didn't choose. Is it ethical to impose this on them? And what happens if, after a few generations, the descendants decide they don't want to continue the mission? What if they want to turn back or change course? These are unresolved questions. So, where does all of this leave us? We've explored the distances, the propulsion challenges, the energy requirements, the hazards of space, the biological and psychological difficulties. We've looked at Proxima Centauri, the nearest star, a star with planets, potentially even habitable planets. And we've confronted the reality that reaching it, even with optimistic assumptions about future technology, is extraordinarily difficult. Not impossible, but bordering on it. And Proxima Centauri is the closest star. If we can barely reach it, what hope do we have of exploring the galaxy? The Milky Way contains somewhere between 200 billion and 400 billion stars. Most of them are hundreds or thousands or tens of thousands of light years away, even traveling at a significant fraction of light speed. Reaching them would take centuries or millennia. Exploring the galaxy would take millions of years. We talk about space exploration as if it's our destiny. As if humanity is meant to spread out among the stars, colonizing new worlds, encountering alien civilizations, building a galactic empire. Science fiction has painted this vision for over a century. Shows like Star Trek, movies like Star Wars, books by Isaac Asimov and Arthur C. Clarke, all depict futures where interstellar travel is routine. where ships zip between stars in days or weeks, where civilizations span multiple star systems. It's a compelling vision. But the reality is far harsher. The distances are too vast. The energy requirements are too high. The technological challenges are too great. We may be confined to our solar system for the foreseeable future, not because we lack the will or the curiosity, but because the universe simply doesn't permit easy travel between stars. This is sometimes called the Fermi paradox. Enrico Fermi, the physicist, famously asked, "Where is everybody?" If the galaxy is full of stars, and many of those stars have planets, and some of those planets might have developed life, and some of that life might have become intelligent and technological, then where are the aliens? Why haven't we seen evidence of them? One possible answer is that interstellar travel is simply too hard. If we, with all our technology and ambition, find it nearly impossible to reach even the nearest star, perhaps other civilizations face the same barrier. Perhaps the galaxy is full of civilizations, each confined to their own star system, unable to communicate or visit each other because the distances are too great. We're all islands, isolated by the vast ocean of space. This is a lonely thought. It suggests that the universe, for all its size and grandeur, is a place of profound isolation, that intelligent beings, if they exist, are doomed to solitude, unable to ever meet or share their knowledge and experience. But there's another way to think about it. Maybe the challenge of interstellar travel is what makes the universe interesting. Maybe the very difficulty is what gives meaning to our efforts. If reaching another star were easy, it wouldn't be an achievement. It wouldn't inspire awe or wonder. The fact that Proxima Centauri is so close, just 4 light-years away, and yet so far unreachable with current technology, forces us to confront our limitations. It reminds us that the universe is not built for our convenience. It doesn't care about our ambitions or our dreams. It operates according to laws that are indifferent to us. And yet, we keep trying. We keep designing spacecraft, proposing missions, developing new technologies. We keep looking up at the stars and wondering what's out there. Because that's what humans do. We explore. We push boundaries. We attempt the impossible. Even if Proxima Centauri remains out of reach for decades or centuries, the effort to get there drives innovation. It leads to new technologies, new scientific discoveries, new ways of thinking about our place in the universe. And maybe, just maybe, one day we'll find a way. Maybe we'll develop propulsion systems we can't currently imagine. Maybe we'll discover new physics that allows us to circumvent the light speed barrier. Maybe we'll build artificial intelligence that can survive the long journey and explore on our behalf. Or maybe we'll accept that some things are beyond our reach, and that's okay. That the stars, for all their beauty and mystery, are meant to be admired from afar. That our destiny is here, in our solar system, on this planet, and perhaps on the other worlds orbiting our sun. There's plenty to explore right here. Mars, the moons of Jupiter and Saturn, the asteroid belt, the Kuiper belt, the Oort cloud. These are places we can reach with current or near-future technology. Places where we can build habitats, conduct science, search for life. The solar system is vast. It would take lifetimes to explore it fully. And maybe that's enough. Maybe we don't need to reach other stars to have a grand adventure. Maybe the journey is here, in our cosmic backyard. Let's dig deeper into what makes this barrier so absolute. Let's look at the actual numbers in even more detail, because understanding the true scale of the problem requires confronting the mathematics head-on. We talked about the Parker Solar Probe reaching speeds of about 430,000 miles per hour. That's roughly 0.06% of the speed of light. At that speed, the journey to Proxima Centauri would take about 6,600 years. But the Parker Solar Probe only achieves that speed when it's diving close to the Sun, using solar gravity as a slingshot. It can't maintain that speed indefinitely. As it moves away from the Sun, it slows down. For a journey to Proxima Centauri, you'd need a propulsion system that can maintain high speed throughout the journey. The fastest spacecraft ever launched in terms of escape velocity from the solar system is Voyager 1. Voyager 1 was launched in 1977. It flew past Jupiter in 1979 and Saturn in 1980, using gravity assists from both planets to increase its speed. Currently, Voyager 1 is traveling away from the Sun at about 38,000 miles per hour. That's fast by any earthly standard. But in cosmic terms, it's a crawl. At this speed, Voyager 1 would take about 73,000 years to reach Proxima Centauri, if it were headed in that direction, which it's not. Voyager 1 is headed toward the constellation Ophiuchus in a completely different direction. But even if we redirected it toward Proxima Centauri, it would take 73 millennia to get there. 73,000 years ago, modern humans had just begun to spread out of Africa. We were hunter-gatherers, living in small tribes, using stone tools. We hadn't invented agriculture, writing, cities, or any form of advanced technology. The entire span of recorded human history, from the first writing systems to the present day, is only about 5,000 years. Voyager 1's journey to Proxima Centauri would take 14 times longer than all of human civilization has existed. This puts the problem in stark perspective. Even our fastest current spacecraft is hopelessly slow for interstellar travel. And it's not like we can just build a faster one by scaling up current technology. The problem is fundamental. Chemical rockets, the kind we use to launch everything from satellites to the space shuttle to Mars rovers, are limited by the energy density of their fuel. The best chemical rocket fuels can achieve exhaust velocities of about 3 to 5 miles per second. That's the speed at which the exhaust gases leave the rocket nozzle. To go faster, you need to carry more fuel. But more fuel means more mass. And more mass means you need even more fuel to accelerate that mass. The rocket equation, formulated by Konstantin Tsiolkovsky in 1897, quantifies this relationship. It shows that the final velocity of a rocket is proportional to the exhaust velocity times the natural logarithm of the ratio of initial mass to final mass. In simpler terms, to achieve a given speed, you need to carry a certain amount of fuel. To double that speed, you don't need twice as much fuel. You need exponentially more fuel. The relationship is logarithmic, which means it gets harder and harder to go faster. For example, let's say you want to build a rocket that can reach 10% of light speed. That's about 18,600 miles per second. If your exhaust velocity is 5 miles per second, which is about the best you can do with chemical rockets, the mass ratio needs to be enormous. You'd need a rocket where 99.999% of the total mass is fuel, and only a tiny fraction is the actual spacecraft. This is physically impossible. You can't build a structure where essentially all the mass is fuel. The rocket itself, the engines, the fuel tanks, the structure to hold it all together has mass. And once you account for that, the numbers don't work out. This is why chemical rockets can't take us to the stars. They're great for getting off Earth, for reaching orbit, for traveling to the Moon or Mars. But for interstellar travel, they're useless. So, what about other propulsion methods? Let's look at nuclear propulsion in more detail. Nuclear thermal propulsion uses a nuclear reactor to heat a propellant, usually liquid hydrogen, to extremely high temperatures. The hot hydrogen expands and is expelled through a nozzle, creating thrust. Because nuclear reactions release much more energy than chemical reactions, you can achieve higher exhaust velocities. A nuclear thermal rocket might achieve exhaust velocities of 5 to 10 miles per second. Better than chemical, but still nowhere near what you need for interstellar travel. To reach even 1% of light speed using nuclear thermal propulsion, you'd still need impractical amounts of fuel. Nuclear electric propulsion is a variation where the nuclear reactor generates electricity, which is then used to power an ion drive or plasma thruster. These drives can achieve much higher exhaust velocities, 20 to 60 miles per second, or even higher. The problem is that they produce very little thrust. They're efficient, meaning they use fuel slowly, but they accelerate slowly too. An ion drive might take months or years to accelerate a spacecraft to high speed. For interstellar travel, you'd need to run the drive continuously for decades just to reach a meaningful fraction of light speed. And you'd still need enormous amounts of fuel. Then there's nuclear pulse propulsion, the idea of detonating nuclear bombs behind your spacecraft. Project Orion, studied in the 1950s and 60s, envisioned a spacecraft with a large pusher plate on the back. You'd eject a nuclear bomb, detonate it, and the explosion would hit the pusher plate, driving the spacecraft forward. Repeat this thousands of times, bomb after bomb, and you could reach high speeds. Calculations suggested that an Orion spacecraft could reach 3 to 5% of light speed. That would get you to Proxima Centauri in about 80 to 140 years. Still a long time, but much better than thousands of years. The engineering challenges are massive. The pusher plate needs to withstand the repeated shock waves of nuclear explosions. The spacecraft needs to carry thousands of nuclear bombs. Each explosion needs to be precisely timed and positioned. And there are enormous political and environmental concerns. Detonating nuclear bombs in space or Earth's atmosphere would violate multiple international treaties. The radiation from the explosions could damage the spacecraft's systems and cargo. And launching a spacecraft loaded with thousands of nuclear warheads from Earth's surface is a recipe for disaster if anything goes wrong during launch. For these reasons, Project Orion was never built. But it remains one of the few propulsion concepts that could, in principle, achieve a significant fraction of light speed using technology that's at least theoretically possible. Fusion propulsion is another possibility. Fusion, the process that powers the sun, involves fusing hydrogen nuclei into helium, releasing tremendous amounts of energy. If we could build a fusion rocket, it could potentially achieve exhaust velocities of a significant fraction of light speed. A fusion rocket using deuterium and helium-3 as fuel might achieve exhaust velocities of 10 to 20% of light speed. That would be a game changer. But we don't have fusion reactors yet. We've been trying to build them for over 70 years. The problem is that fusion requires extremely high temperatures and pressures. You need to heat hydrogen to tens of millions of degrees and confine it long enough for fusion reactions to occur. On the Sun, gravity provides the confinement. The Sun's enormous mass creates the pressure needed to sustain fusion. On Earth, we don't have that luxury. We need to use magnetic fields or inertial confinement to hold the plasma in place. Experimental fusion reactors, like ITER, the International Thermonuclear Experimental Reactor being built in France, are designed to demonstrate sustained fusion reactions that produce more energy than they consume. But ITER won't be operational until the late 2020 sets at the earliest. And even when it works, it will be a stationary power plant, not a rocket engine. Adapting fusion for propulsion adds a whole new layer of complexity. You need a fusion reactor that's compact and lightweight enough to put on a spacecraft. You need to control the fusion reactions precisely to produce thrust. You need to deal with the intense radiation produced by the fusion process. These are all solvable problems in principle, but in practice, we're decades or centuries away from a working fusion rocket. And even if we had one, it still wouldn't let us travel at anything close to the speed of light. 10 or 20% of light speed is the best you could hope for. That gets you to Proxima Centauri in 20 to 40 years. A long time, but within a human lifetime. But only barely. And that's assuming the fusion rocket works perfectly, which is a big assumption. Antimatter propulsion represents the theoretical upper limit. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy. This is the most efficient energy conversion possible. E equals mc squared. Every kilogram of matter-antimatter fuel would release about 9 times 10 to the power of 16 joules of energy. For comparison, a kilogram of gasoline releases about 46 million joules when burned. Antimatter is roughly 2 billion times more energy dense than gasoline. With antimatter propulsion, you could theoretically achieve exhaust velocities approaching the speed of light. A spacecraft powered by antimatter could reach a significant fraction of light speed with relatively small amounts of fuel. The catch is that antimatter doesn't exist naturally in any appreciable quantity. You have to produce it in particle accelerators by smashing particles together at high energies. When you do this, occasionally you create a particle-antiparticle pair. But the process is incredibly inefficient. You put in vastly more energy than you get back in the form of antimatter. Current technology can produce only tiny amounts of antimatter, a few nanograms per year, and it costs billions of dollars. Producing even a single gram of antimatter would cost trillions of dollars with current methods. For an interstellar mission, you'd need kilograms or tons of antimatter. The cost would be astronomical, far beyond the resources of any nation or even all nations combined. Even if cost weren't an issue, storing antimatter is another nightmare. Antimatter annihilates instantly upon contact with normal matter. So you need to keep it suspended in a perfect vacuum using magnetic or electric fields. Any containment failure, any power loss, any system malfunction, and your antimatter touches the walls of its container and annihilates, releasing a blast of energy equivalent to a nuclear bomb. Storing tons of antimatter safely for years or decades is a challenge we're nowhere close to solving. So antimatter propulsion, while theoretically possible, is practically out of reach for the foreseeable future. This brings us back to the fundamental problem. All of our propulsion concepts, from chemical rockets to nuclear to fusion to antimatter, face either fundamental physical limits or practical engineering barriers that make interstellar travel incredibly difficult. And we haven't even talked about the biggest barrier of all: the speed of light. According to Einstein's theory of special relativity, nothing with mass can reach or exceed the speed of light. This isn't a technological limitation. It's a law of nature. As you accelerate closer to the speed of light, several things happen. Your mass, as measured by an outside observer, increases. Time for you, as measured by an outside observer, slows down. And the energy required to accelerate you further increases without limit. To actually reach the speed of light would require infinite energy, which is impossible. So, there's a hard cap on how fast anything can travel. Light speed is the universal speed limit. For light itself, photons with no mass, this is the natural speed. But for anything with mass, light speed is unreachable. You can get close. 99%, 99.9%, 99.99%, but you can never quite get there. And the closer you get, the more energy it takes to go just a little bit faster. This means that even with unlimited energy, even with perfect technology, there's a limit to how fast we can travel. And that limit means there's a limit to how far we can explore within a reasonable time frame. Even at 99.99% of light speed, reaching a star 1,000 light-years away would take just over 1,000 years. From the perspective of the travelers, due to time dilation, it might feel like much less time. But from the perspective of Earth, from the perspective of the civilization that sent them, a millennium would pass. This creates a fundamental barrier to exploring the galaxy. The Milky Way is about 100,000 light-years across. To cross it, even at near light speed, would take 100,000 years. Most of the interesting stuff in the galaxy, the dense star clusters, the galactic core, the spiral arms full of young stars, is tens of thousands of light-years away from us. Reaching any of it would take tens of thousands of years. Human civilization is only a few thousand years old. 10,000 years ago, humans were just beginning to domesticate animals and plants. We were transitioning from hunting and gathering to agriculture. The idea of sending a mission that would take 10,000 or 100,000 years is almost incomprehensible. Who would fund it? Who would build it? Who would benefit from it? By the time the mission arrived at its destination, the civilization that sent it would be gone, replaced by something completely different, or perhaps vanished entirely. This is the ultimate barrier to galactic exploration. Not the engineering challenges, not the energy requirements, but the sheer scale of time involved. The galaxy is too big. The distances are too vast. The timescales are too long. We're stuck. Not in our solar system, necessarily. We could probably spread throughout the solar system if we wanted to. We could build habitats on Mars, on the moons of Jupiter and Saturn, in the asteroid belt. We could harvest resources from asteroids and comets. We could build massive space stations, rotating cylinders, providing artificial gravity, housing thousands or millions of people. The solar system is huge. It would take centuries to fully explore and settle. But beyond that, beyond the edge of the solar system, lies the vast emptiness of interstellar space. And crossing that emptiness, reaching even the nearest star, remains one of the hardest challenges imaginable. Proxima Centauri sits out there, tantalizingly close, just over 4 light-years, our nearest neighbor. And yet, it might as well be on the other side of the universe. Now, let's think about what it would actually take to send humans to Proxima Centauri. Not just a probe, but a crewed mission. People making the journey, living on a spacecraft for decades, arriving at another star system with the goal of exploring, perhaps even colonizing. This is the stuff of science fiction. But let's treat it seriously. What would it really take? First, you need a spacecraft large enough to support human life for the duration of the journey. We said earlier that a fast spacecraft might reach Proxima Centauri in 40 to 50 years. That's assuming you can achieve 10 to 20% of light speed. A human crew would need to survive for that entire time. They'd need living space. Not just a cramped capsule like the Apollo command module, but actual living quarters. Bedrooms, common areas, exercise facilities, workspaces. Think of it like a small village or a submarine, but in space. And it needs to be self-sufficient. No resupply missions. No abort option. Once you launch, you're committed. So, the spacecraft needs to carry everything the crew will need. Food, water, air, medicine, spare parts, tools, everything. Or it needs to produce these things on board. For food, you'd probably need hydroponic gardens, growing plants in nutrient-rich water under artificial light. Plants provide food, but they also help recycle air, absorbing carbon dioxide and producing oxygen. But plants need light, and light requires energy. You'd need a significant power source to run the grow lights for decades. For water, you'd recycle everything. Wastewater, urine, even the moisture from the crew's breath. Advanced filtration and purification systems would clean and reuse every drop. The International Space Station already does this to some extent. Astronauts on the ISS drink water that was urine a few days ago. It sounds unpleasant, but the purification systems are so effective that the water is cleaner than most tap water on Earth. For air, you'd need to scrub carbon dioxide from the atmosphere and replenish oxygen. Plants help with this, but you'd probably also need chemical or mechanical systems. Lithium hydroxide canisters, which absorb carbon dioxide, or molecular sieves, which separate oxygen from other gases. All of this requires energy and produces waste heat that needs to be dissipated. Then, there's the psychological aspect. We touched on this earlier, but it's worth exploring in more depth. 40 years on a spacecraft. No going outside. No fresh air. No horizon. No change of scenery except what you can see through a porthole. And what would you see? For most of the journey, nothing. Just blackness. Stars in the distance, but they don't move or change. The sun behind you, slowly fading as you get farther away. Proxima Centauri ahead, slowly getting brighter, but imperceptibly so from day to day. It would be profoundly monotonous. Studies of isolated environments, like Antarctic research stations, submarines, or even prisons, show that humans struggle with prolonged isolation and confinement. People develop depression, anxiety, irritability. Conflicts arise over trivial matters. Some people suffer psychological breakdowns. And those studies involve environments where you can at least go outside occasionally, or where you know the isolation is temporary. On a spacecraft to Proxima Centauri, there's no outside, and the isolation isn't temporary. It's 40 years. You'd need to select crew members who are extraordinarily resilient. People who can tolerate boredom, confinement, and repetition without losing their sanity. You'd need to provide activities to keep them mentally stimulated. Books, movies, games, virtual reality simulations, meaningful work, scientific research, maintenance tasks, social interaction, but not too much. The crew would need to get along, but they'd also need personal space. Too much togetherness can be as damaging as too much isolation. You'd probably want a crew of at least a dozen people, maybe more. Large enough that there's social diversity, but small enough that resources aren't stretched too thin. But even with the best selection and the best environment, there's no guarantee everyone would make it through psychologically intact. And if someone does have a breakdown, what do? You can't send them home. You can't even send them to a hospital. You're years away from Earth, and you're not turning back. You'd need psychiatric care on board, medications, therapies, and you'd need contingency plans for what to do if someone becomes dangerous to themselves or others. These aren't pleasant things to think about, but they're real considerations for a mission of this length. Then there's the question of governance. Who's in charge? On a spacecraft with a crew of a dozen or more, traveling for 40 years, you need some kind of social structure. A captain, a chain of command, rules and protocols. But what happens if the crew disagrees with the captain's decisions? What if there's a mutiny? On Earth, you can call for backup, bring in outside authorities. In space, you're on your own. The crew is the entire society. There's no outside authority to appeal to. Historical examples of long sea voyages show that leadership and social structure are critical. Successful expeditions had strong, respected leaders and clear chains of command. Failed expeditions often descended into chaos, mutiny, or despair. For a spacecraft to Proxima Centauri, you'd need to establish a social structure that's fair, flexible, and resilient. Something that can survive for 40 years without collapsing. That's not easy. Now let's talk about what happens when the spacecraft arrives at Proxima Centauri. After 40 years of travel, the crew finally approaches their destination. Proxima Centauri grows brighter in the sky. Eventually, it becomes bright enough that you can see it's not just a point of light, but an actual disk, a glowing sphere. You're still traveling at 10 or 20% of light speed. The question is, do you slow down or fly past? If you slow down, you need to decelerate. And as we discussed, deceleration requires just as much energy as acceleration. If you spent all your fuel speeding up, you don't have fuel to slow down. So either you carried extra fuel for deceleration, which makes your spacecraft much heavier and harder to accelerate in the first place, or you used some other method to accelerate, like a laser sail, and saved your onboard fuel for deceleration. Let's assume you managed to slow down. You enter the Proxima Centauri system at a more reasonable speed, slow enough to maneuver and enter orbit. What do you find? Proxima Centauri is a red dwarf. It's much dimmer than the Sun, but up close, it's still impressively bright. From the distance of Proxima B's orbit, about 4.5 million miles, the star would appear larger in the sky than the Sun appears from Earth, because you're much closer to it. But it would also look different. Red dwarfs emit most of their light in the infrared spectrum. To human eyes, Proxima Centauri would look dimmer and redder than the Sun. The light would be a deep orange or red, casting everything in an eerie, sunset-like glow. Your spacecraft approaches Proxima B. This is the planet in the habitable zone, the one with the potential for liquid water. You deploy instruments, take measurements. What do you find? Does Proxima b have an atmosphere? Does it have water? Does it have life? These are the questions that drove the mission in the first place. But the answers might be disappointing. As we discussed earlier, Proxima b is likely tidally locked. One side always faces the star. The other side always faces away. The day side would be hot, the night side cold. If there's an atmosphere, it might redistribute heat somewhat, creating a habitable twilight zone between the two extremes. But if the atmosphere is too thin, or if it's been stripped away by stellar flares, the planet could be a barren wasteland. Even if there is an atmosphere, the composition might not be breathable. It could be mostly carbon dioxide, like Venus, or methane and ammonia, like the outer planets. Without oxygen, humans couldn't breathe it. And even if there's oxygen, the planet might be covered in toxic chemicals or bombarded by radiation from stellar flares. The truth is, we won't know what Proxima b is like until we get there, or until we develop telescopes powerful enough to study it in detail from Earth. And that's the gamble of an interstellar mission. You're committing 4 decades of travel, enormous resources, and human lives to explore a destination you know very little about. It's possible the crew arrives and finds a lush, habitable world with breathable air and liquid water. A second Earth. But it's also possible they find a dead, irradiated rock with no atmosphere and no hope of supporting life. And if that's the case, what do? They can't come home. They don't have the fuel to make the return journey. They're stuck in the Proxima Centauri system. They could try to survive in orbit, living on their spacecraft indefinitely. But the spacecraft was designed for a 40-year journey, not for permanent habitation. Systems would start to fail. Resources would run out. Eventually, the crew would face impossible choices. This is the dark side of interstellar exploration. The possibility that you arrive at your destination and find nothing worth the journey. And there's no way home. You're committed. For better or worse, Proxima Centauri becomes your new home. Even if it's inhospitable. Even if it's deadly. That's a terrifying prospect. And it's one reason why sending humans on interstellar missions is so much more difficult than sending probes. A probe can be a one-way mission. It explores, sends back data, and then its mission is complete. But humans need to survive. They need a place to live, a way to continue their existence. If the destination doesn't provide that, they're doomed. This is why many scientists argue that the first interstellar missions should be unmanned. Send probes first. Study the target star system in detail. Determine if it's worth sending humans. Only then, once you know what's there, do you commit to a crewed mission. But that adds time. You send a probe. It takes 40 years to arrive. It studies the system for a few years, then sends back data, which takes another 4 years to reach Earth. So, you're looking at nearly 50 years before you even know if the destination is worth visiting. And by then, technologies might have advanced. You could build a better, faster spacecraft. So why send humans at all if the probe already explored everything? This is another paradox of interstellar exploration. The timescales are so long that the missions become obsolete before they're complete. Now, let's consider a different scenario. What if we don't try to send humans at all? What if instead we send genetic information and build humans at the destination? This is the concept of a seed ship. Instead of carrying adult humans, you carry frozen embryos or even just DNA. Along with the genetic material, you carry artificial wombs and robotic systems capable of growing and raising children. The spacecraft arrives at Proxima Centauri, lands on a suitable planet, or establishes a space station, and begins the process of creating a new human population from scratch. Robots would raise the first generation, teaching them language, culture, science, and survival skills. Once that generation reaches adulthood, they could reproduce naturally, establishing a permanent colony. This approach has several advantages. You don't need to keep adult humans alive for 40 years. You don't need as much food, water, or living space. The spacecraft can be smaller and lighter, but there are enormous ethical questions. Is it right to create children who have no parents, who are raised by machines, who have no connection to Earth or human civilization except through recorded messages? Is it right to impose this existence on them without their consent? And what happens if something goes wrong? If the robots malfunction, if the planet turns out to be uninhabitable, if the children can't survive without adult guidance? You're creating human beings in a hostile, alien environment with no support system. It's a huge gamble with the lives of people who don't even exist yet. Some philosophers and ethicists argue that this is morally unacceptable. Others argue that it's no different from having children on Earth. Every parent brings a child into a world without that child's consent, into circumstances the child doesn't choose. The debate is unresolved, but it highlights the ethical complexities of interstellar colonization. There's also the question of what happens to the human species if we do establish colonies on other stars. Let's say we successfully send missions to Proxima Centauri, Barnard's star, and a few other nearby systems. Over centuries or millennia, we establish dozens or hundreds of colonies on planets orbiting different stars. Each colony is isolated. Communication between them takes years or decades, depending on the distance. Travel between them is nearly impossible. Over time, the colonies would diverge. They'd develop different cultures, different languages, different technologies. They'd adapt to their local environments, which might have different gravity, different atmospheric composition, different day-night cycles. Over thousands of generations, they might even evolve into different subspecies or species. Humans on a high-gravity planet might become shorter and stockier. Humans on a low-gravity planet might become taller and thinner. Humans on a planet with intense radiation might develop thicker skin or more robust DNA repair mechanisms. Eventually, the colonies might become so different that they're no longer recognizable as the same species. Humanity would fragment into a diaspora of related but distinct groups, each adapted to its own world. Would they still consider themselves human? Would they still identify with Earth and the species that originated there? Or would they become something new, something alien? These are questions we can only speculate about. But they're worth considering. Because if we do become an interstellar species, if we do spread to the stars, we'll be fundamentally changing what it means to be human. We'll be diversifying, adapting, evolving. And the unity of humanity as a single species might be lost. That's both exciting and terrifying. Exciting because it represents the ultimate exploration, the ultimate frontier. Terrifying because it means the end of humanity as we know it. We'd be creating something new, something we can't predict or control. And once we start down that path, there's no turning back. So, where does all of this leave us? We've looked at chemical rockets, nuclear propulsion, fusion, antimatter, laser sails, generation ships, sleeper ships, and digital uploads. Every approach has problems. Fundamental problems, engineering problems, ethical problems. There's no easy answer. No magic bullet that makes interstellar travel straightforward. And that's the reality we have to accept. Proxima Centauri is 4.24 light-years away. That distance, small as it sounds in cosmic terms, represents a barrier that we may never overcome. Not because it's impossible in principle, but because the practical challenges are so overwhelming that they might as well be impossible. We can dream about reaching the stars. We can design spacecraft on paper, run simulations, calculate trajectories. But building the actual hardware, launching the actual missions, that's a different matter entirely. It requires resources, energy, time, and political will on a scale that's hard to imagine. And even if we had all of that, even if every nation on Earth came together and devoted their entire economies to building an interstellar spacecraft, we'd still be limited by physics. By the speed of light, by the rocket equation, by the sheer vastness of space. These aren't problems we can engineer our way around. They're fundamental properties of the universe. And they mean that the stars, for all their beauty and mystery, may remain forever out of reach. Now, you might be thinking, this is all very pessimistic. Isn't human history full of people declaring things impossible, only to be proven wrong? People said heavier-than-air flight was impossible. The Wright brothers proved them wrong in 1903. People said breaking the sound barrier was impossible. Chuck Yeager did it in 1947. People said going to the moon was impossible. Apollo 11 landed there in 1969. So why couldn't interstellar travel be the same? The difference is that flight and space travel within the solar system don't violate fundamental laws of physics. They're just engineering challenges. Difficult engineering challenges, but solvable in principle. Interstellar travel, on the other hand, runs into hard limits. The speed of light, the energy requirements, the distances. These aren't just engineering problems. They're constraints imposed by the structure of the universe itself. Now, it's true that our understanding of physics could be incomplete. Maybe there are loopholes, ways around the light speed limit that we haven't discovered yet. Wormholes, for instance. Theoretical shortcuts through spacetime that could connect two distant points. If wormholes exist and can be stabilized, you could potentially travel from Earth to Proxima Centauri instantaneously. But wormholes are purely theoretical. They arise as solutions to Einstein's equations of general relativity. But that doesn't mean they actually exist in nature. And even if they do exist, stabilizing one would require exotic matter with negative energy density. We've never seen such matter. We don't know if it exists. So wormholes, while fun to think about, are not a practical solution. The same goes for warp drives. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a way to travel faster than light by warping space-time around a spacecraft. It's a clever idea, and the mathematics work out, at least on paper. But there are problems. It requires negative energy density, the same exotic matter we mentioned with wormholes. The amount of energy required is enormous, possibly more than the mass energy of the entire observable universe. And there are causality problems. Faster-than-light travel can lead to time travel paradoxes. So, while the Alcubierre drive is mathematically consistent with general relativity, it's not clear that it's physically realizable. The point is, we don't currently have any proven way to circumvent the light speed limit. We can speculate about wormholes and warp drives and other exotic concepts. But speculation isn't the same as a working technology. Until we discover new physics, we're stuck with the limits we know. And those limits mean that reaching even the nearest star is extraordinarily difficult. So, maybe the answer is that we don't reach the stars. Maybe we accept our place in the solar system and focus on what's achievable. There's plenty to explore right here. Mars is a fascinating world with a complex geological history. It once had liquid water on its surface. It might have harbored life in its distant past. We could send humans there within the next few decades. The moons of Jupiter and Saturn are equally intriguing. Europa has a subsurface ocean beneath its icy crust. That ocean might contain life. Titan has lakes of liquid methane on its surface and a thick atmosphere. These are missions we could accomplish within our lifetimes. They don't require breakthrough technologies or unimaginable amounts of energy. They're hard, but they're achievable. Maybe that's enough. Maybe we don't need to reach the stars to have a grand adventure. Maybe the solar system is our playground, our domain, and that's okay. We could spend centuries exploring every moon, every asteroid, every comet. We could build habitats in space, massive rotating stations housing millions of people. We could mine asteroids for resources, build solar power arrays, terraform Mars. We could become a true spacefaring civilization without ever leaving the solar system. And maybe that's our destiny. Not to spread across the galaxy, but to fully inhabit and understand our own corner of it. But the dream of reaching Proxima Centauri persists. And maybe it should, because even impossible dreams serve a purpose. They push us to innovate, to discover, to reach beyond what seems achievable. The quest to reach the stars has already given us technologies we use every day. Satellite communications, GPS, weather forecasting, all came from space programs. Materials science, computer technology, medical devices, all advanced because we tried to send humans to the moon. The attempt to reach Proxima Centauri, even if it never succeeds, will drive innovation in propulsion, energy production, life support systems, materials engineering. It will force us to solve problems we didn't even know existed. And those solutions will have applications here on Earth. That's the value of pursuing the impossible. Not necessarily achieving it, but learning from the attempt. Growing from the challenge. Becoming better, smarter, more capable as a species. So maybe we should keep dreaming about Proxima Centauri. Keep designing missions, even if we never build them. Keep studying the star, learning about its planets, imagining what it would be like to go there. Because in reaching for the stars, we reach for our own potential. We push ourselves to be more than we are. And even if we never leave our solar system, even if Proxima Centauri remains forever unreachable, we'll have become something greater in the trying. We'll have expanded our knowledge, our capabilities, our understanding of what it means to be human. And perhaps that's the real journey. Not across light years of space, but across the boundaries of our own limitations. Not to distant worlds, but to new frontiers of science, technology, and human achievement. But Proxima Centauri will always be there, shining faintly in the southern sky. A reminder of what lies beyond. A challenge we may never overcome, but also a symbol of something profound. Think about what it means that we even tried to understand Proxima Centauri, that we built telescopes powerful enough to detect it, even though it's invisible to the naked eye. That we measured its distance with extraordinary precision, that we discovered planets orbiting it, that we calculated what it would take to reach it. All of this represents an amazing achievement. We're a species that evolved on the savannas of Africa, adapted to hunt and gather, to survive in a world of predators and prey. Our brains developed to solve immediate problems. Find food, avoid danger, cooperate with our tribe. We didn't evolve to understand light years, or calculate rocket equations, or contemplate the nature of space and time. And yet, we do. We've extended our understanding far beyond the immediate, the tangible, the visible. We've reached out with our minds to comprehend things millions and billions of miles away. Things we'll never touch, never visit, but can still understand. That's extraordinary. The fact that we know Proxima Centauri exists, that we know it has planets, that we can calculate the distance to within a fraction of a light year, is a testament to human ingenuity. We've done this despite being confined to one small planet. We haven't sent spacecraft there. We've simply observed it from afar, collected photons that have traveled 4.24 years to reach us, and extracted information from those photons. Information about the star's mass, its temperature, its composition, its motion through space. Information about its planets, their orbits, their masses, their potential habitability, all from particles of light. That's the power of science. We can understand distant worlds without ever visiting them. We can know things about the universe that no other species on Earth knows or could know. We can look up at the night sky and see not just points of light, but entire solar systems, each with its own story, its own history, its own potential. And that knowledge enriches us. It gives us perspective. It reminds us that Earth, for all its importance to us, is just one small world in a vast cosmos, that the Sun is just one star among hundreds of billions, that our galaxy is just one galaxy among trillions. We're small, insignificant in the grand scheme of things. But we're also remarkable. We're the universe becoming aware of itself. We're matter that has organized itself in such a way that it can observe and understand the cosmos that created it. Even if we never leave the solar system, even if Proxima Centauri remains forever out of reach, we've still accomplished something amazing just by understanding it. And maybe that's the real journey. Not the physical journey to distant stars, but the intellectual journey to understand them, to map the cosmos, to unravel its mysteries, to comprehend our place within it. That journey has no barriers. It's limited only by our curiosity, our creativity, our willingness to ask questions and seek answers. We can't travel to Proxima Centauri with our bodies. Not now, maybe not ever. But we can travel there with our minds. We can study it, learn from it, incorporate it into our understanding of the universe. And in a sense, that's a form of exploration too, because knowledge lasts. Physical journeys end. Spacecraft break down, missions conclude, explorers return home or are lost. But what we learn endures. It gets passed down through generations, built upon, refined, expanded. The knowledge we've gained about Proxima Centauri, about exoplanets, about the nature of stars and space and time, that knowledge is permanent. It's part of human civilization now. It will inform everything we do going forward. So maybe the distance to Proxima Centauri, the impossibility of reaching it, is teaching us something important. Maybe it forces us to be more thoughtful, more careful, more deliberate. If interstellar travel were easy, we might rush into it without fully understanding the implications. But because it's hard, because it might be impossible, we're forced to confront who we are and what we want before we can even attempt it. We're forced to solve our problems here on Earth. We're forced to mature as a species. Proxima Centauri is there, 4.24 light-years away, close enough to detect, to study, to dream about, far enough to remain a mystery, a challenge, a reminder of our limitations. It's the perfect distance, in a way, close enough to inspire us, far enough to humble us. And maybe we will reach it someday. Maybe in 100 years, or 1,000, or 10,000. We'll develop technologies we can't currently imagine. Maybe our descendants will make the journey. They'll arrive at Proxima Centauri, explore its planets, establish a presence there. And when they do, they'll look back across 4 light-years of empty space and see the sun, our sun, as a faint point of light in their sky. And they'll remember where they came from. They'll remember the species that first looked up at the stars and wondered. The species that built telescopes and spacecraft and dreamed of reaching other worlds. The species that understood the distance, comprehended the challenge, and tried anyway. That's us. That's humanity. Small, fragile, confined to one tiny planet in a vast and indifferent universe. But curious, ambitious, relentless in our pursuit of knowledge and exploration. We may never reach Proxima Centauri. The challenges may prove too great, the distances too vast, the laws of physics too constraining. But we'll keep looking up. We'll keep studying the stars. We'll keep pushing the boundaries of what we know and what we can do. Because that's what we do. That's who we are. And even if the stars remain forever out of reach, the fact that we tried, the fact that we understood, the fact that we cared enough to ask the question, that matters. That's the legacy we leave. Not cities on distant planets, but knowledge, understanding. The recognition that we're part of something larger than ourselves. Part of a universe that's ancient, vast, and filled with wonders we're only beginning to comprehend. A reminder of what lies beyond. A challenge, a mystery, a beacon. 4 light-years away. So close, in cosmic terms, and yet, perhaps, forever out of reach. Tonight, we've confronted one of the hardest truths about the universe. That distance matters. That space is not just empty, it's vast beyond comprehension. That the nearest star, the closest possible destination beyond our solar system, represents a barrier that may prove insurmountable. Not because the laws of physics forbid us from reaching it, but because the practical challenges, the energy, the time, the technology required, are so immense that they might as well be infinite. Proxima Centauri is there. It has planets. One of them might even be habitable. It's the closest star to our sun, a mere stone's throw in galactic terms, and yet it might remain forever beyond our grasp. That's the universe we live in. Beautiful, mysterious, and profoundly isolating. And understanding that, truly grasping what it means, changes how you see everything. Thank you for joining me on this journey through space and time. If you found this exploration valuable, a like or subscribe would mean a lot. It helps this channel keep exploring the cosmos and sharing these ideas with curious minds like yours. Remember, the stars are out there, shining in the darkness. And even if we can never reach them, we can still look up and wonder. That wonder, that curiosity, is what makes us human. Good night. And may the stars, distant as they are, continue to inspire you.